morning, everybody. Welcome back to Galois Theory for our second to last day of class. How are y'all doing today?
Second to last day.
Is that sadness or happiness? Like, what is?
Or both.
That's the question, isn't it?
Yeah. Hi, Lady YouTube. Plan for today. We're gonna talk some more about solvability by radicals and see if we can get to our proof of the insolvability of the quintic today.
On the second to last day.
Yeah. Oh, we need to talk about the formal Galois correspondence theorem, I suppose.
Are you setting this to write the final?
Well,
We each contribute one problem.
Oh, that's a long final.
I don't want to grade that. No, that's just me making a note to myself that I should actually write your final.
Let Lincoln write a problem.
Please no.
No. That's as horrifying to me as it is to most of the class. Office hours, Thursday, this afternoon 1 to 2, tomorrow at 11, Monday 11 and 1, and at some point your final will appear, and I'll make sure you have at least a week to work on it. Any questions or comments before we get started for today? Is that a...
What?
Okay. Donut.
It's
That was
purpose by
backwards.
word
If you
extension.
hassle that wordless or question to the final, who would you choose?
That was not awkward.
If I had to have one of you write the question for the final, who would I choose? That's a tough one. You have like the most power over it. I think I'm gonna go with Eleanor.
That's dangerous.
Literally every answer, there is no non-dangerous answers to this question.
Here.
No, I think he could give a good singer of a problem. I wouldn't put it past him. He wouldn't do it just to be like for the sake of giggles, but like I could see him giving
The problem with doing it with Eleanor is we know everything is going to be at max 4.
yeah, which is why I feel the most comfortable with it.
It's gonna be in CMOD 4.
All right. Eleanor, give me a problem I'm happy with by the end of the day tomorrow, and I'll give you a bonus point on the final.
Okay. Sounds
All right, and with that, let's hop to it.
Can we all do that?
No.
Oh.
If you want to give me a problem, you can. And if it is good, I will give you a bonus point. But
Okay.
that does apply to everyone in the class
Okay.
if it actually gets used. End of the day tomorrow. Make it happen. It's not just Eleanor now. I gotta be fair.
Oh, now you have to be fair.
Well, I should be fair all the time, but sometimes I pretend like I'm not. And sometimes I'm not, actually. All right, let's get back to it. So last time, we finished up our discussion of what it means for a group to be solvable and some properties thereof. And we also talked about what it means for a function, a polynomial, to be solvable by radicals. Where essentially we said that a polynomial is solvable by radicals if we can build a radical extension, which is just take the base field and keep adding nth roots of things until you get to something that contains a splitting field for your polynomial. And what we were doing last time was we were in the middle of proving that if you have a field of characteristic 0 and f of x has a solvable Galois group, then f of x has to be solvable by radicals, giving us, in other words, a relationship between these two notions of solvable, having a solvable group and having a polynomial that is solvable by radicals. Turns out the relationship is through the Galois group. So last time we got like halfway through this, so just to kind of briefly summarize what we did. So we had this nice diagram. K is our base field. L was a splitting field for our polynomial f of x. We need to use this lemma, and which says that K is a splitting. K is a field of characteristic 0 where you have where xcm minus 1 splits completely, and you have a cyclic extension of K of degree m. Cyclic means the Galois group over K is cyclic. And L is a splitting field of some polynomial of the form xcm, let's say. So last time we said we have some f of x. L is our splitting field of f of x. E is going to be a splitting field for x to the m minus 1, where m is we said m was the degree of the Galois extension, or the Galois group, L over k. We said, all right, let E be a field in which x to the m minus 1 splits, and we had this nice fun diagram where both of these contain E intersect L, which contains K, and we said that E is going to be M is a splitting field for f of x over E. We got this nice diagram. We had that the Galois group of M over E was isomorphic to the Galois group of L over E intersect L for reasons we didn't really talk about, but said it was something similar to second isomorphism theorem. And then we used the fact that Galois group of L over K solvable to say that, hey, that means that the Galois group of L over E intersect L has to be solvable because Galois group of L over that is a subgroup of the Galois group of L over bit, and subgroups of solvable groups are solvable. And then since this is isomorphic to something that's solvable, that told us that the Galois group of M over E is solvable. And so then we use this to come up with a tower of subgroups. That went from E, which is our G naught, normal subgroup of G1, normal subgroup of G sub R equals G. G being this thing, where each G sub I plus 1 mod G sub I is abelian. And then we use the Galois correspondence to say that, hey, that leads us to a nice sequence of subfields between E and M. So we get this nice K. K is a subfield of, the tower really starts at E, which is equal to some M sub R, which is a subfield of M sub R minus 1, which is a subfield of bit, which is a subfield of M naught equals M. And where the Galois group of M over M sub I is equal to G sub I for each I, using the correspondence of the fixed fields from the Galois correspondence theorem for each I with the Galois group of M sub I over M sub I plus 1 going to be isomorphic to G sub I plus 1 over G sub I. Okay, that's where we left things off this time. I left off a lot of words on the board, but we were kind of halfway through a somewhat lengthy proof. All right, questions or comments thus far? Good, seeing none, let's move on. So, we have this kind of tower of normal subgroups going from trivial subgroup up to G, which is the Galois group of M over E. We also have this corresponding sort of tower of subfields, field extensions of E that live in between E and M, and they kind of have this nice Galois correspondence. So now what we're going to do is we're going to look at these guys and talk about some properties that they have. So we're going to say for each I, we're going to let D sub I be equal to the degree of the extension M sub I over M sub I plus 1. So basically, the degree of the extension of, because each of these is an extension of the one that comes before it, so let's just take the degree of each of those. And then I claim each D sub I has to divide the degree of the extension M over E. Why is that? James?
It's an extension of that degree thing that we did a really, really long time ago that for a
Degree extension is multiplicative.
Yeah, degree extension is multiplicative. That's a good way to put it.
Yeah, because we said that the degree of the extension m over e is going to be equal to the degree of the extension of m over the one that comes before it times the degree of the extension of the one that one of the one that comes before it, which is equal to that times the degree of the extension that one times over that, which is equal to the degree of the extent times the degree of the extension, excuse me, that one over that one.
Just a quick question.
Ma'am.
Does the order matter that it's mi on the left and mi plus 1 on the other on the right? Or?
Yeah, because that is a subfield of that. Because if you kind of look at this, as the subfields get bigger,
Right, I forgot we wrote them in
subfields are
backwards
getting
order.
smaller. Yeah, we wrote it, and we did that because of the having to flip the lattice upside down for
Yeah,
the
I
Galois
forgot we flipped
correspondence.
it backwards. Okay.
That does matter, but it is. But I was thinking about that as I wrote it. Like, wait, is that actually correct? Oh, yes, it is, because we did it backwards. So each d sub I divides the order of m sub e, which is the order of m over e, which is equal to size the Galois group of m over e, which divides in turn the degree of the Galois extension of L over K, which is M.
Sorry, I feel like this is an obvious question, but how do we know that the degree of this extension is the same as the degree of the Galois group? Is that generally not always the case?
It's generally not the case, but it's the fact that it comes from the fact that our f of x is irreducible, and basically saying that like going from e to m, we're taking we're taking a splitting field of f of x,
Okay.
and so any of the roots can map to. Wait, why is this?
That's supposed to be the degree of them.
Let me think about this.
M is just a number.
And it's
The degree of m over e, you mean, or
what does it have?
Wait.
what,
No, I
what
just-
is this?
There's like M
The Galois group,
This is why I need to. This
the
is why I
degree
need
of the
I feel like there's-
Galois group is equal to m. What's m there? Is that an m we've used?
So this little m is just
we have a little
it's
M
the
and a
degree.
big M.
So
Oh,
this
I'm
little m
sorry.
is the degree of this
I
Galois
read
extension.
that as
Because
big
it's
M.
times
I read that as
instead
big
of
M.
having to-
Sorry.
Instead of having to be equal.
I think that's the case. Yeah, I think that definitely has to divide that. Yeah. Does it have to be equal? I'm not convinced, but since all that we really need is that it divides, because we're going to say each d sub I divides m here in just a second. We can just go with divides.
This is probably a dumb question. Stumps Dr. Gerstl.
No, it was a good question. Yeah, after you made me look at it, I'm like, why is that? And I feel like there's a good reason that it's not occurring to me off the top of my head. But it definitely does divide,
Right.
which is what we're going to need.
Okay.
So here's a question: why does that have to divide that?
That was actually the question I was going to ask, but I was like, is this a dumb question? But
This one I actually have an answer for. Jonah?
We say that M for E is isomorphic to L over E.
Which in turn is a subgroup of L over K. And so by Lagrange's theorem, the order of this, since this is a subgroup of that, the order of this has to divide the order of that. And since these are isomorphic, they have the same order, therefore order of this has to divide order of that.
Lagrange's theorem.
Lagrange. All right, so everything divides. All right, so the d sub I all divided is kind of what we're getting at here. Now, what's next? We're going to say since m sub I plus 1 contains E, and E contains all the mth roots of unity for some splitting field of xcm minus 1, and that just came about from how we defined the field extension E yesterday. E was an extension of K in which we had all of our nth roots of unity. M sub I plus 1 contains E. It contains each nth root of unity. And since d sub I divides m by what we showed in the paragraph above, that means m sub I plus 1 must contain each d sub ith root of unity. How does that work? Well, if you contain an nth root of unity, so let's say you contain some value alpha, where alpha to the m is equal to 1. Well, since d sub I divides m, we can write that m as being equal to d sub I times some k, which is equal to alpha to the k power of d sub I. And so if
Which means d sub I is something to, or is something raised to the power of d sub I is equal to 1.
yes. Andrew's giving me a frown and that scares me.
Why does it mean that that particular subgroup must contain the dith root of unity? Because clearly m contains the dith root of unity, but why does m sub I plus 1?
Well, since m sub I plus 1 contains the nth roots of unity, and d sub I divides
Okay.
this
Okay.
thing that contains the nth roots of unity also has to contain the d sub ith roots of unity. If I ever teach this class again, it's not going to be my 32nd class in a row.
What?
No notice to myself. All right,
Third consecutive class. So
here we go. We're finally getting ready to use this lemma here.
the lemma that Lydia cannot.
Oh, Lydia, there's a lemma over on the sideboard. It's the lemma that I had for this theorem that I wrote on the board at the end of last class. Look at the previous video, please. I don't know if Parker's going to
You want me to do?
Lydia, would you like him to?
I think she
I
would.
didn't hear a yes.
You didn't hear a no either.
Oh, I did. Okay, fair enough.
Oh, you're gonna wait for it?
Oh, man.
Oh no.
Right where I was about to write, Parker.
You can write,
Still
you
right.
can still see.
Yeah, there you go. It just turned off.
And since
You're gonna get jumped.
Scott log of m sub I over m sub I plus 1 is cyclic and contains all, wait for it, degree of m sub I over m sub I plus 1 roots of unity
Oh, it didn't jump scare. It's fine.
what
I thought the screen was just gonna turn on automatically, but no, it's actually taking.
Probably because I was using it this morning and I taught it in the boss then. Alright, so each Galois group m sub I over m sub I plus 1 is cyclic. Oh, here's where we need, by the way, that it's isomorphic to this tower of subgroups. And here is where we need for our solvable groups that if something is solvable, then in the tower of subgroups we can force each one of these subsequent quotients to be cyclic specifically. So we're
The
using,
quotients are the Galois group?
well, these are just subgroups of the Galois group.
But,
Quotients of subgroups of the Galois group.
okay, but the quotient is cyclic, why does that mean the Galois group is cyclic?
It doesn't mean the Galois group is cyclic, but it means each one of these is cyclic, which means each one of these is cyclic, is what I'm getting at.
Because
Because they're
they're
isomorphic.
Ah.
Because things that are isomorphic to cyclic things must also be cyclic. And contains all m sub I over m sub I plus 1, which the degree of this extension is what we just called d sub I. Roots of unity. Our lemma tells us,
The lemma that is, do you mind if I pan over to?
go for it again.
It's probably
That lemma, our lemma tells us, man, Parker's really looking out for you, Lydia.
that one.
I wouldn't baby you as much as he does.
That's because you're.
Tells us that for some beta sub I, an element of m sub I with beta sub I root of x to the power of d sub I minus c, where c is some element in m sub I plus 1. M sub I is equal to m sub I plus 1 extended by beta sub I. Whew. Okay, that's a mouthful. What did we just do? Well, we said that since each of these is cyclic, and we know something about the degree of this extension, basically we're replacing M in the lemma with D sub I here, and saying that since this Galois group is cyclic, and since it also contains all the D sub I roots of unity for whatever our D sub I happens to be for that particular I, well, the lemma kicks into play and then says that M sub I has to be a splitting field over M sub I plus 1, specifically a splitting field for something that's of this form. So in other words, M sub I we can get from just taking the previous term, M sub I plus 1, and adjoining some radical. The D sub I root of the corresponding C is probably C sub I. Whew, that's a mouthful. So what does that tell us? Well, if you actually stop and think about it, actually tells us everything we need. Tells us f of x is solvable by radicals. Because we just handled all the M sub i's and showed that each extension to get from k all the way up, to get from e to all the way up to m, or from k all the way up to m, is we're just extending each time by some nth root, technically some d sub ith root of something of this form in our extension. So from here, we can kind of conclude immediately f of x is solvable by radicals.
I have one line on my second page.
Aren't you special?
I have a whole past second page.
I mean, I use my whole second page pretty much,
I
but
did it on one page, but it's totally unreadable.
all right, that's a question. I know a question I'm going to be putting on the final event. Thanks for that idea, Parker.
That's the problem.
Can
is
you
that
read your own
Does he-
notes?
does
Is
he
that the
get
question?
I'm sorry, John, what were you saying?
And does he get a point?
Sure, 1 out of 1 point back for the 10 points he's going to be missing on that question. So it turns out, so main takeaway I want you to have from this is the relationship between solvability of groups and solvability by radicals of polynomials. If your polynomial has a solvable Galois group, then your polynomial necessarily has to be solvable by radicals. So what about the other way around?
I don't know.
Turns out the other way around also works.
Oh, yeah.
Well,
Here's our next theorem.
Oh, another thing.
this is so much shorter.
Is it?
Well, it's so much shorter because we're not actually proving the next one.
Oh,
Because the next-
Doesn't even have a page, so it's like, oh, that's
Because,
nice.
and the reason why is because the proof of the other direction is like twice as long as this proof was.
Oh, nice.
Wait, half the length and twice the length. That's not right.
Well, it is if you're not trying to actually if you're trying to skip over the proof.
He just wants to give examples. As is obvious to the casual observer.
Yeah, there.
Let K be a field with characteristic 0, and let K be a subfield of L, which is a subfield of M, where M is a radical extension. Tubular. Alright.
You're still right. We can do it.
So is this?
I can't say no to Calbook. I love the Ninja Turtles.
There you go.
Then the Galois group with L over K is solvable.
Is that for any L?
Yeah.
Intermediary stuff?
Well, any L between K and M.
Yeah.
Yeah.
Great.
You won't consider radical.
If L is contained in any radical, if L is contained in any radical extension of K, if L is an intermediate field, then the Galois group of L over K has to be solvable.
Oh yeah, I know why that works.
That feels like a very simple logic to be honest.
Actually,
Sure.
so-
Well, essentially, it's the opposite argument of what
Yeah.
we did there.
Well, yeah.
This argument gave us a way of saying solvable Galois group means solvable polynomial by radicals. This one, on the other hand, is giving us a way to say solvability by radicals implies solvable Galois group.
I just realized this is stupid. Remind me what characteristic means.
How many times do you have to add 1 to itself before you get to 0?
Thank you.
It's really
If it happens in a finite number of steps, say that's your characteristic. If it never happens, then it's characteristic 0. Clap. So for instance, K can be Q here, but it can't be Z mod PC.
What if it happens with a certain
It's not
probability?
I don't know what that means.
what?
I don't know what that means either.
So basically you're saying suppose we don't have a well-defined operation.
No, we have a probabilistically defined.
Oh.
Okay, moving on.
It might be defined.
My head hurts enough already.
It's sometimes defined.
That sounds good.
So here's a corollary. If we combine these two theorems, we get that polynomial f of x over k with k having characteristic 0 is solvable by radicals.
Schrodinger's got one.
And both is characteristic 0 and not 0 at the same time.
Yeah.
If and only if the Galois group of f is solvable. Okay. And that is the end of this packet. Yeah, we're not proving this theorem because, like I said, it's long. It's kind of it's longer and more tedious than this one. It's in the book though, if you want to check it out. And it has some good math to it. The reason I'm skipping it is not because I don't think it's worth doing. It's because I think it's not worth doing with the small amount of time we have
The
left
1.5
with each other.
classes remaining.
Don't remind me. Andrew.
Is there like a reason that we have like L in between K and M instead of just?
It's to give us a more generalizable result.
Okay.
Like, this certainly works in the case where L equals M, and that's kind of what we're using as far as the corollary goes. But the theorem here actually does work in a little bit more generalization, and so that's why we're including it that way. Ready? That way. Pardon?
Where's that Schrodinger 0 that you just put there? There you go.
It looks amazing.
All right, Eleanor.
So by the Galois group of F, you mean a
The Galois group of L over K, where L is a splitting field of F.
okay, awesome. Just double check.
Yeah. Whenever we say Galois group of a polynomial, what that really means is take a splitting field for that polynomial, then take the splitting field over your base field, and that's your extension for which you're taking the Galois group. Relying, of course, on the fact that splitting fields have to be isomorphic to each other, otherwise that would not be well defined.
Yes.
But
It's just that simple.
it is just that simple. All right. Next packet. Second to last packet of the semester.
But what is this?
You better get all the way through this packet today.
We're probably not, but next packet won't be a super long one.
Oh, so
Finally ready to tackle the quintic
Woo!
using some of our results. So we're going to use this corollary. The fact that this is an if and only if statement means that if you have a polynomial whose Galois group is not solvable, then that polynomial is not solvable by radicals. So what we're going to be doing in this packet is we're going to be we're going to be wrangling ourselves a polynomial whose Galois group is not solvable, which means that polynomial is not going to be solvable by radicals.
Are we gonna stick with characteristic 0?
We're going to be doing it over Q.
Okay.
Whenever someone talks about the insolvability of the quintic, they mean over Q.
But we could do it.
I mean, if you wanted to do it over Z mod PZ, this result no longer works, so good luck with that.
Yeah.
So, here's the deal. Here's the sitch. What example have we seen of a group that is not solvable? S5. Sn for n greater than or equal to 5 if you want to generalize, but yeah. So what do we need to do? Show that the quintic equation is not generally solvable by radicals. We just need to find ourselves a polynomial of degree 5 whose Galois group is S5.
And we only need one because it's proving the negative, right?
Yeah, we're just proving, yeah, because there's lots of degree 5 polynomials you can solve by radicals.
We're just proving that.
For instance. But when we say the quintic is not solvable by radicals, we mean
All of them.
Generally.
there's at least one that is not.
And then that suffices to show for all greater numbers because we can just multiply by any.
Essentially, yeah. It essentially turns out that for n greater than 5, yeah. You can't, it doesn't quite suffice in and of itself because you can't necessarily say that a degree 6 or higher is a product of a degree 5 and a degree.
No, but you can create ones that couldn't be solved.
But you can certainly create ones that can't be solved, yes. Which we'll take a look at. So, before we go on to finding actually finding a polynomial whose Galois group is S5 directly is a little bit bleh. So we're going to have a couple intermediate results before we actually do that. Start with, there's a lemma for you. S sub n is generated by 2 cycles in particular. The 2 cycle 1, 2, and the n cycle 1, 2, 3, n.
Why is that just one? Or why not just have the second?
Because that does not give you all of Sn. This will only give you n cycles in the identity element. If you take the subgroup generated by that n cycle right there,
Oh, I missed. Okay, I missed that.
you can't get 2 cycles out of it, for instance.
I missed that n was in complement with the Sn.
Oh, gotcha. So this is the
I was thinking cycles of.
yeah. So this is all permutations of the numbers 1 through n. This is the cycle that maps 1 to 2, 2 to 3, 3 to 4, n minus 1 to n, n to 1. And it turns out you can get a bunch of cycles out of this. In fact, you can get n of them, I would dare say. If you just keep multiplying by itself and its inverses, but it won't give you all of Sn because you won't be able to just switch 2 elements, for instance. That's what 1, 2 is for. But it turns out if you have a subgroup of Sn that happens to contain both of these cycles, then that subgroup will necessarily be all of Sn. So that's that one. So here's a proof. We're going to be referring to these a lot, so I'm just going to give this the name sigma and this the name tau. Nope. I'm going to give this the name tau and this the name sigma. Let's not confuse ourselves. Alrighty. So then what would we get if we took sigma tau, sigma inverse?
Is it a sorority or a frat?
Well, it's an inverse of a sorority or frat, so what's the inverse of Greek life?
Conjugate of.
Roman life?
Healthy.
No.
Not drinking.
Well, we would get 1, 2, 3, all the way up to n.
Do alpha.
1,
Oh,
2.
yeah.
And then n minus 1, 2, 1. Because we're taking inverse. So.
Yeah, no, I just got sigma and tau.
So, let's look at 1. Where does 1 map to? 1 maps to n, which maps to n, which maps to 1. Oh, hey, 1 maps to itself. Whoa!
That was kind of cool.
Where does 2 map to? 2 maps to 1, which maps to 2, which maps to 3.
Whoa.
Where does 3 map to? It maps to 2, which maps to 1, which maps to 2. Where does 4 map to? 4 maps to 3, which maps back to 4. And it turns out everything else just maps to itself, so we end up with a different 2 cycle 2, 3. Whoa.
I bet you could make every 2 cycle this way.
Well, you can make it, well, it gets a little more complicated than that, but that's essentially the idea.
Yeah, because you just do.
You put in 2 3s.
Yeah, you just.
So, if we were to do this
There we go.
Oh.
There it is.
like that, let's say,
Oh, gosh.
Oh yeah.
let's do it like this actually.
Have a town sigma half.
So if we took So if we basically took powers of sigma and did this, what would you expect to get? Hint, powers of sigma, well, powers of sigma that are not the identity map. So if, assuming k minus 1 is less than n, sigma to k minus 1 is a different n cycle. Parker?
My first guess would be, I mean, for greater and greater k's, you get the two cycles that go further and further. So would it be k plus 1?
It would indeed. By generalizing. And you could do this, I mean,
Proof by induction.
yeah, I was gonna say this is a quick inductive proof if you wanted to do it that way, but it's not too hard to show. So great.
Wait,
So
is it k plus 1, k plus 2?
oh, it's k plus 1 because we're taking sigma to the k minus.
Oh, you
Yeah,
stuck the
you
minus 1 there.
Yeah. I stuck a minus 1 in there, otherwise you'd be right.
Wait, so is that, sorry, is that sigma to the k minus 1?
Yeah.
So
Yeah,
then k plus
I should actually try and write this so it's readable, possibly.
legibility.
Let's try that.
That's important.
And then what's the power on the other sigma?
Negative k plus 1. So, in other words, we're doing this, but instead of having one copy of sigma and sigma inverse on each side, we have k minus 1 copies of them. So great, that gives us all two cycles of the form an element k goes to k plus 1. So if we have sigma and tau, we have everything that looks like this.
But there are more cycles.
Unfortunately, that's not everything, so we still have some more work to do.
Shucks.
Didn't we show that Sn was generated, no, An was generated by 3 cycles? What was it we showed was generated by 3 cycles?
8 of them.
Okay, isn't S of n generated by 2 cycles?
It is.
So we're done? We've got all of the
We would be
generated
done if
elements?
we knew that all 2 cycles were contained in our subgroup.
Ah,
But we don't have all 2 cycles yet. We have 2 cycles that look like this.
We could have.
But we
can
could have one that,
combine
like-
them creatively to make them into all the 2 cycles?
That's what we're about to do. Yeah, I mean you're not wrong. Yes, that is all we need, but it's not obvious just from this point
Yeah,
yet.
as Jason said,
That we would have all 2 cycles, for instance.
like 2, 3, and 3, 4 make 2, 4, don't they?
Yeah. Well, let's say this. For j greater than 1, I want you all to know what happens if we do this.
Is that j minus 1 or I?
J's.
Yo.
Science.
So now we're going to multiply a whole bunch of things of this form together.
Oh my lord.
My
Did you get
science.
the?
Well, things are gonna cancel out.
Yeah.
Well, let's see what maps to what. 1 maps to itself, which maps to itself, which maps to itself, which maps to itself, which maps to 2, which maps to 3, which maps to 4, which maps to 5, which maps to 6, which maps to blah, 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 which maps to j minus 1, which maps to j, which maps to j plus 1. 1 is going to map to j plus 1 here. So what does j plus 1 map to? J to j minus 1, to j minus 2, to j minus 3, to 1, to 1, to 1, to 1, to 1, to 1. It's like 1 to 1, but on steroids. To 1, to 1. And it turns out everything else gets mapped to itself. Because
That's highly confusing.
because everything else doesn't need this term in the middle, ends up not using this term in the middle. And if it doesn't use this term in the middle, well then wherever it maps to from these terms, it's gonna these terms is going to unmap it to, map it back to where it started.
There's only one term involving 1.
Yeah, there's only one term involving 1, but there's 2 terms involving, 3 terms for 2 and 2 for everything else.
It's a beautiful machine.
It is a beautiful machine.
It's a machine.
There you go, Emily Rose. That gives us a bunch more 2 cycles. That gives us all 2 cycles of the form 1 mapping to
Okay,
something.
1 I and 1 j. What is that?
3 cycle.
Right.
So let's go one step further.
What if you did sigma inverse, but with that thing?
What if I did what now?
What if you did we gotta get stuff that's not just.
Oh, sigma times this thing times sigma inverse?
Yeah, that thing.
Yeah.
Because then it'll get you 2
As a matter of fact, we can even say for j less than n minus k, we can rewrite as sigma to the k minus 1 times 1 back into j plus 1 times sigma to the 1 minus k. So basically, we're basically doing the same thing we did to get from here to here, but we're starting with 1 back into j plus 1 instead. Turns out
Why do
that
sigmas look so much like sixes?
because
Because
I hate myself and I hate you.
Schrodinger sigma.
That's going to give us that. Basically, multiplying by powers of sigma on a sigma on the left and a sigma inverse on the right takes our 2 cycle going from 1 to j plus 1 and shifts everything over to the right by 1. So if we were to multiply by sigma on the left once and sigma inverse on the right once, 1j plus 1 would go to 2j plus 2. If we did it again, it would go to 3j plus 3. And so if we do it k minus 1 times, it'll go to k plus j.
The same number, okay.
That's all of them, right?
And now we have all of our 2 cycles because k and j can be anything less than n. Yes.
But now what about everything that's not two cycles?
Sigma and tau generate all 2 cycles.
Well, everything else is a product of 2 cycles.
And since the 2 cycles generate Sn, sigma and tau must generate Sn. Cool. Questions, comments, concerns?
So nifty proof.
Yeah, it's sort of a nifty proof. You just start with like these 2 things and you start looking at what fun and clever ways can we combine these things to get more and more 2 cycles until eventually you're able to show that you get all possible 2 cycles. And once you have all 2 cycles, since 2 cycles generate Sn, I don't feel like proving that right now. That means that Sn is generated by these 2 elements specifically. I'm going to say we did prove that in 410.
Yeah,
I'm pretty sure.
I do recall. I don't recall the proof though, so.
I recall
It involves more of doing this sort of thing where you're multiplying 2 cycles together in clever ways, get whatever arbitrary cycle you want, and once you have all arbitrary cycles, then you have all arbitrary products of cycles, which means you have Sn. All right. Here's our next theorem of the day. Let P be prime and f of x in over Q be a monic irreducible polynomial of degree P with exactly 2 non-real roots and complex numbers. Then f of x has a Galois group isomorphic to SP.
I heard of the day and I just realized something. Did you tell your joke of the day?
Oh, is Dr. On capable of learning trigonometry? No. Actually, no. That's my 105 class. Is Dr. Trelaw capable of teaching geometry?
Whoa.
Of course he can't.
Are you
I feel like I don't get that.
changing
Of
your
course he
lab
can't. You know,
today?
Of course he can't.
You meant trigonometry, not
Cosecant.
Oh, did I say geometry?
Yeah.
You did.
Oh, I meant
You
trigonometry.
said
sorry.
trigonometry the
Yeah, you
first
said
time.
geometry.
Yeah.
Yeah.
Stop and play with me.
Well, they're basically the same thing anyway.
That's
One of them is just a method of doing the
Man,
other.
local man
Oh,
turns
yes.
into a plant.
all right. So let's look at this thing.
It's not funny.
You don't want to be prime?
It's not
I
funny.
don't even know what you said. I just saw your reaction.
I'm just gonna keep writing and talking, and whatever happens, happens.
Oh, okay.
I'm not convinced,
Local
but okay.
mathematician turned
Monic
into a
irreducible
plant.
polynomial of degree P.
It's not that funny. That's a Gerstle joke.
Still don't get
We're
it.
going to suppose f of x has exactly 2 roots.
It's the end of the semester, Parker. Everything is funny.
And the complex numbers outside of the reals.
No, I can't write them.
And in that case, then the Galois group of F is isomorphic to SP. So, what is this theorem going to allow us to do? Well, it's going to allow us to say, take a degree, I don't know, P equals 5, I think 5 is prime, polynomial, and any degree 5 polynomial that has exactly 2 non-real roots, and that's irreducible, has to have a Galois group isomorphic to SP, which is not solvable, implying that that polynomial is not solvable by radicals.
Are ones that have no roots in the complex numbers solvable by radicals?
I challenge you to give me a degree 5 polynomial with no complex roots.
Right, that makes sense.
Wait, sorry, what was that?
Or any other degree, or any other non-constant polynomial for that matter.
Well, you can't construct one?
Well,
That, yeah,
Oh, you mean, well, irreducible, yes.
yeah.
Well,
I guess anyone that's irreducible is just
Well,
a product of
if
smaller
it's
ones.
reducible, you can also find roots of it, so. Lincoln, I said polynomial, not power series, or power product.
Polynomial.
It's a polynomial. Yeah.
I'm writing jokes.
All right, so let's prove this theorem. How are we doing? Oh, we have lots of it. Expected. All right, so starting things off. So this is something that's specific to the rational numbers. So we're going to need our characteristic zeros stuff, right, Eleanor? Right, Seamus?
Yes.
Right, Emily Rose?
Uh-huh.
Good. So we're going to let L, this subset of the complex numbers, be a splitting field for f of x. Then we can say immediately something about the Galois group of f of x. We can say that G, which is going to be our shorthand for the Galois group of L over Q, must permute the p roots of f of x in L. Because remember, automorphisms of L over Q have to map elements, roots of irreducible polynomial to roots of the same irreducible polynomial. So our Galois group is going to be determined by our p roots are mapping, or our p roots are mapping to other roots. So we can immediately say, and we can also say that each root is distinct. There's no repeated roots. Question: why do we know we don't have any repeat roots?
Wouldn't it be reducible if there were repeated roots since we're in R?
Yes, it would be reducible because any extension over Q is going to be separable.
Forgot about that one.
Meaning mill polynomials or irreducible polynomials can't have repeated roots.
Right.
Yeah. Right, each root is distinct since L over Q must be separable. Then G is that let's permute the p roots of f of x and L, where each root is distinct since that is separable, implying right away what relationship between G and SP?
G is a subgroup of SP.
G has to be a subgroup of SP. Or isomorphic to a subgroup of SP, however you want to call it, if you associate the p roots with the numbers 1 through p. The reason being, oh, actually, Andrew, why don't you explain?
Because we can define a homomorphism from, well, I guess we just take every G and we say it's isomorphic to whatever it does. Like, if we treat the roots of F as the elements 1 through P, and then it will permute those. So,
Yes.
and each one will, a different Galois group will permute them differently because they generate the whole thing.
Different automorphism, you mean? Or?
Yeah, sorry.
Okay. Yeah, each automorphism in the Galois group of L over Q is determined by where it maps the roots of f of x. And since there's p of them, there's basically every automorphism is uniquely determined by these p roots are mapping to which other p roots. Well, if we associate the roots, like let's say alpha 1 and alpha 2, alpha p, with the numbers 1, 2, all the way up to p, then a permutation of these p roots is equivalent to a permutation of the numbers 1 through p. So you can kind of associate every automorphism of L over Q with some permutation of the numbers 1 through p, in other words, an element in SP. Jonah.
Wait, how do we know that they must be separable?
Because every extension over Q is separable. We proved that when we first talked about separable extensions. Well, I think we proved that every extension of field of characteristic 0 is separable, which includes Q. Because the one time we ran into a non-separable extension is when we had that freshman exponentiation show up with that kind of nasty example of, let's take z mod pz adjoint t as an extension of z mod pz extended by t to the p. And we were able to show that that was a non-separable extension, and I said that was kind of the simplest example that there was, even though it looked kind of horrendous. Yeah. So right away, though we know G is a subgroup of SP, we don't necessarily know G is equal to SP yet. Because it's not necessarily the case that any permutation of these roots will give us an element of the Galois group necessarily. There could be some relationship between these roots that would cause certain permutations to not be homomorphisms. Or certain would-be permutations to not be homomorphisms, I should say.
But those rely on complex roots.
Those are somehow going to rely on complex roots, yes.
If you only have 2 of them, limits the amount of degrees of freedom you have.
That's the key idea behind what's going on here, yeah. So let's write this out a little bit more formally. So in constructing out, we're going to let alpha be some element in the complex numbers with a minimal polynomial, have a minimal polynomial of f of x. And we're going to consider Q adjoint alpha. We know that since f of x is irreducible, we can construct some element in our splitting field for which f of x will be the minimal polynomial. Well, I mean, just find some complex number that'll do that. So we're just going to call that alpha, and we're going to look at the extension of Q just by that alpha for the time being. And if we do that, well, then it turns out if we want to look at the degree of the Galois group of L over Q, well, we can use Seamus the theorem I think you were trying to reference earlier, the one that said kind of extension degrees break up nicely.
Yeah.
We can break this up into order of the Galois group of L over Q of alpha multiplied by Galois group of Q of alpha over Q. Which, I don't know what this necessarily is. But I do know what this is.
Should be 2, right?
2. Why 2?
Because alpha is a complex root.
Of a degree, it's a complex root of a degree p polynomial,
Oh,
where p is prime.
so it's P.
It's going to be p. It's going to be p homomorphisms in there.
So we know that the thing on the top works for field extensions?
Yeah, how do we know that that works for Galois groups as well? It turns out that's a consequence. Yeah, it turns out that's not exactly the same theorem that Chivos was mentioning earlier. Similar to. This comes as kind of a consequence of the Galois correspondence theorem. If you take apart the Galois correspondence theorem and just sort of look at degrees of like different levels of the lattice, you got this result.
Okay.
Which I was wondering if someone was going to say that, but glad you did, because if not, I was going to. I don't want to write down that result in full because it's cool. We got stuff to do.
Yeah, no problem.
But that's that's where that comes from. I'll just make it clear. Which in turn tells us that P has to divide the order of the Galois group. Hardest time I'm having with writing this proof is figuring out how many parentheses I need to close.
Yeah, this is not JavaScript.
It's not JavaScript, no. So
Tell you?
here we're going to use a theorem. So here we're going to use a theorem that's sort of from 410 that I know Andrew has seen, but I don't think those of you who had me for 410 we ever talked about. Cauchy's theorem.
Pharma science.
Which Cauchy's theorem, though.
I don't know. Pick your favorite.
There's so many of them.
Cauchy's integral theorem, Cauchy's integral formula, Cauchy Riemann, but no. We're going to use a theorem that says, that's sort of like a corollary of the Silo theorem, Andrew, that says if you have a prime number that divides the order of your group, you have to have an element in that group of order P.
I think we did actually mention that 14.
I think we may have mentioned it, but I'm pretty sure we didn't prove it.
We didn't prove it.
But I
Yeah, because it kind of uses some more advanced group theory theorems, the Silo theorems, which we didn't talk about just due to lack of time. But we're not going to talk about it now, and I'm just going to say, then by Cauchy's theorem, Cauchy, Galois group of L over Q must have an element of order P, since P divides the order of the Galois group. Let's give this element a name. And we can call it tau of order P. Now, G is a subgroup of SP, right? What do elements of order P in SP look like?
Are they the P cycles? The ones that
There's no others. You're correct. It is.
Okay,
It is all
I
P
don't
cycles.
think there are.
You just sounded very unsure, so I thought I would ask. Yeah. Since G is a subgroup of SP, this means G contains a P cycle. Contains a P cycle. Oh, of course. Look ahead 2 lines in my notes and I'm calling it sigma. Why not? Next page is blank, by the way. I'm moving on to the next page in my notes.
Wait, what does it mean that G contains a P cycle? Given that P cycle G is
Well, it contains something. It contains.
Cycle of order.
Well, you know what a P cycle is in SP, right?
yes.
So G contains an automorphism that acts as a P cycle does. It maps root 1 to root 2, root 2 to root 3, root 3 to root 4, ... root P to root 1 for some ordering of the roots.
P cycle and quotation in scare quotes in your head.
I just wrote P cycle automorphism on my notes.
Sure. It's an automorphism that acts as a P cycle does.
And this is, of course, a different P than the P we're using in the beginning of the proof.
Oh, it's the same P.
It's the same P?
We're using this is building towards the lemma.
F of
We
X.
need to show that it has 1, 2, and a P cycle.
Well,
and
I
that'll
did not.
generate the whole.
I did not.
SF.
I showed no such thing.
What?
I didn't show we have a 2 cycle.
We haven't yet. I said we're going to do that next.
Oh, you said okay. I thought you said we already did that.
No, I said we're building towards using the lemma.
Yeah, we're building towards using the lemma. We've shown that we have a P cycle. That's going to be our 1, 2, all the way up to P. Now we need to show we have the corresponding 2 cycle as well, and then the lemma will immediately tell us it's
That it's
SP.
Isomorphic.
But it's isomorphic to SP. Whatever. So, next step. So, something that we haven't actually used yet. We haven't actually used yet anything about like the fact that we have exactly two roots that are outside of R. We're going to use that here. And we're going to say that since the two non-real roots of f of x have what relationship? F of x is irreducible polynomial over Q. We have two complex roots. What relationship, Eleanor, do those two roots have to satisfy?
They're conjugates.
They're complex conjugates of each other, and we proved that like a couple months ago at this point. Back when we were first talking about why does irreducibility over R come down to just degree 1 and degree 2.
We didn't say it was the fundamental theorem of algebra and that we forbidden
No,
complex.
we showed it.
We did show it?
Yeah.
Yeah, we showed that one. Yeah, we actually had to construct an argument. I think part of fundamental theorem of algebra was saying that was when we said irreducibility over Q or over C, it means
It's linear.
linear. Yeah, which was part of our proof that irreducibility over R is linear or quadratic. But it wasn't used as part of the proof of the property Eleanor mentioned, that roots of real polynomials that are complex have to be conjugate pairs. So these must be complex conjugates of each other. Say that since that happens. One element in G must just swap those two roots and leave everything else alone.
Hold on. What could that possibly
That's not like a
create?
2-cycle.
That couldn't possibly create like no.
That would be kind of goofy.
How do we know that? Well, complex conjugation is a homomorphism. You take the complex conjugate of all your roots, the ones that are in R just get mapped to themselves. The two non-real roots are going to map to each other. So we have an element in G that swaps two things and leaves everything else alone. What does that mean G has to contain? Thus G contains a 2-cycle.
Oh! Hey, wait. It's got a 2-cycle and a p-cycle.
Yeah.
Wait a minute. Hey,
Yes.
now hold on just a second.
What can we do with that?
I don't know.
Can we apply our lemma?
I don't know. Maybe we can.
Maybe we can. Or maybe we can't because the lemma didn't say an arbitrary 2-cycle and an arbitrary p-cycle generate SP. It was two specific ones.
This is true, but
Did
I feel
it-
like it doesn't.
But it can generalize probably.
You're right. True. It ends up not mattering.
Is it Wallon kind of thing or?
Well, right now we're going to say we'll log. Let denote this 2-cycle by 1, 2.
I love Wallons.
Whoa.
So basically, we're saying if we're listing out our roots, the p roots of our original f of x, just let the not ones outside of R be 1 and 2.
Because didn't we kind of say like?
And we will log again over here.
Can't necessarily log over here because our p cycle, whatever our p cycle is, doesn't necessarily map 1 to 2, for instance.
Except it does.
There are 2
because
p-cycles out there.
you there's only 2 roots. So you just take the minimal polynomial, like degree 2, that has the 2 roots that are the complex conjugates of each other. So we have that.
Sure, but that's not necessarily going to give us a p cycle or be part of the p cycle, is it?
Well, but those are the only. So if your minimal polynomial is degree 2,
Well, but can we
Then-
also just?
you have to then it has to
Oh, I-
map those roots to. There's only 2 roots.
I see what you're getting at. You're taking a look at just the minimal polynomial, like in this extension of like the one thing. Yeah, you can make an argument that way. There's a little bit of work to do, but I think you could make an argument that way.
Then 1 would have to map to 2, and 2 would have to map to 1, so you just don't have.
Yeah, that doesn't necessarily. Yeah, there's a lot of work. I think I can see where you're getting at, Isaac, and there's a way to do that. It's kind of hard and involves a lot more work, involves some extra stuff. There's an easier way to get around this. Eleanor, sounds like you had an idea.
I had an idea, but then I wasn't sure.
Well, let's hear it. So we got a p cycle, and we have the 2 cycle 1, 2 specifically.
Can't you multiply the p cycle by itself to get something that's in the
Yeah.
form?
Yeah, we have a p cycle. The p cycle sigma might not map 1 to 2, but if we keep taking powers of that p cycle, eventually it will map 1 to 2. And then 2 will map to something else, which we can call 3, and 3 will map to something else we can call 4. And well, in other words, while this p cycle might not be of the form 1, 2, 3, ... right now, some power of it will be, which gives us what we need. Let's write that down.
Because the p cycle.
So now, let's consider
This sounds like arcade.
sigma, which right now, sigma is just a p cycle, which means we can write it in the form 1 a sub 2, a sub 3, up through a sub p, where a sub 2 through a sub p are some ordering of the numbers 2 through p. We know one of these terms is 2, so we're just going to call one of these terms, we're going to say a sub k is equal to 2. We know that because this is all p, all numbers 1 through p, so 2 has to be in there somewhere. Well, then if we take sigma to the k minus 1, we'll get 1 mapping to 2, because each time we multiply, or we compose sigma with itself, 1 is going to map to 1 term out further in this cycle than it originally did.
Sounds like the last problem on the final for real analysis that we did, or abstract. Wait,
Didn't we do something like that?
did we or not? Well, because remember that card problem we did?
Yes.
Oh, that was fun.
Something.
Yeah.
Oh, the car. Oh, that wasn't the final. That was the midterm.
It was the
Yeah.
Oh, it was the midterm.
And
It's very related.
now,
Yeah.
since 1's mapping to 2, now we'll log it and say it's of the form 1, 2, 3, ... p. Because whatever comes after the 2, we haven't assumed anything about these other than it's 3 through p in some order, so we can just relabel them and call that 3 through p. Well, without lossing around the sigma to k minus 1 and 1 and 2. All the way up to p, which is an element in G. Wow, indeed.
That is, wait, is it
Now we can
isomorphic
use-
to an element, or,
It's isomorphic. Okay, fine. It's isomorphic to an element in G. Look, I'm playing fast and loose with the rules because I'm a dirty prof who sticks it to the man.
Who don't stick it to the man.
That's what I'm doing. But yes, technically you're right. That means that with our isomorphism between G and whatever copy of S sub P we're looking at, or whatever subgroup of S sub P, we're looking at, G is going to contain that corresponding element. So yeah, the isomorphic element, whatever. But I'm just going to say thus, the 2 cycle 1, 2, and the p cycle 1, 2, 3, but then the p are elements of G. Hence, G is equal to S sub P. I'm leaving it as equal to just to spite you.
I'm putting the little curly.
I put the curly.
You do what you want.
/con.
If this was Math 410, I'd be more careful about it, but at this point, I've given up on you all, so.
Slash con.
There. Does that make you feel better?
Yes.
Okay.
You can add another-
Say what?
you can add another squiggly.
No. Alright, so
We're twice that.
we're basically there now, because if we combine everything we've done over the last week or so, we just need to find a polynomial of prime degree who's with exactly 2 non-real roots, where p is at least 5. Can anybody think of such a polynomial?
How about the one on the next page?
How about that? X to the 5th minus 8x plus 2.
That's an interesting looking polynomial.
Yeah,
Crazy. Wonder who came up with such a weird polynomial.
I don't know. Who do you think?
You know what to do.
Dr. Trelawney?
I don't actually know. It was in the textbook, so. So let's look at an example here. F of x equals x to the 5th minus 8x plus 2. So, first of all, why is this thing irreducible? Lincoln, I already heard you say.
Eisenstein with P equals 2.
Yep. F of x is irreducible over q by Eisenstein with p equals 2. 2 does not divide our leading coefficient. It does divide negative 8 and 2. 2 squared does not divide our constant term of 2. Therefore, by Eisenstein, this thing is irreducible over q. Let's look at I don't feel like finding roots of this thing, so let's look at a graph. Oh hey, the graph looks like this.
Zooey mama, that's like 3 real roots.
Yeah, that's like 3 real roots. So how many non-real roots?
So 2 of them.
2.
Yeah.
Oh my goodness. What? Crazy.
Oh my side.
Smack him. So we get 2 roots in the complex numbers outside of the reals. Yes, they're necessarily.
You can use the sign. The sign rule.
You can use Descartes' rule of sign
Yeah.
that there's at least 3 roots, and then you can show that there's only 2 places where the first root is 0.
Sure. I don't know. Do whatever you want. Use intermediate value theorem or Descartes. You can use whatever you feel like to produce this graph and see if there's 3 roots. Yeah. Whatever. I don't care. I don't care for the purpose of this question, which in turn implies
Complex.
that the Galois group of f of x is what?
It's more than S5.
It's equal to S5.
Crazy.
Which we showed,
Yes.
that was last class, which is not solvable.
It's insoluble as it will.
Or insoluble, as the book puts. I don't know. Every time I see soluble, like makes me think we're doing chemistry. Looking at like solvents and such, which is like solvable. I think is like the American way of doing it. Soluble is more of like an international way. I like solvable better because I don't ask you to. I don't come into like a Calc 1 class and say, hey, here's an equation. I want you to solve for x.
We're dissolving it.
So you put it in a- you put it in a
That's where it actually comes from, yes. But I don't know. I don't
Oh,
know.
wait, really? Oh.
Don't
I
know.
mean, is there some way to use the like solution in both?
Yes.
The,
Oh.
Find the solution. Yes. I mean, all these words are related to each other. Yes.
I've never thought about that.
Which, by the theorem we had earlier today, means that f of x
Oh, right, and then
is
product.
not solvable by radicals.
Whoa.
Oh, right, because you get products in chemistry too.
you do.
I bet Dr. Billman comes in and he's a
Yeah.
math nerd. Look, I'll get a smiley face in the box.
Whoa. And
Look,
then
look, we did it. Insolvability of the quintic. Yay!
Insolubility of the quintic. Come on.
So we
In
can't
chemistry,
solve
alcohol is a solution.
So how does this work for anything greater than the quintic that is not a
Why'd you
prime?
I don't know, maybe we'll have to look at the next couple pages in the packet. Oh gosh, we're gonna have to do that and
Especially organic, because
I don't know if we're gonna have time for the full course.
it. Need a lot of.
Alright, that's it for today. Next time we will end the course with a bang.
so you can generate things
Turns out-
just by multiplying by something.
Okay.
By something you know this.
And bye ladies.